All right. So just a short second video for this skill. In the direct variation in skill number 7, we solved them with proportions, but we also talked about the idea of setting, or rather finding a constant of variation and using that to sort of solve your problems. That technique still kind of exists here. It's not my favorite because you kind of end up doing the same work with an extra step in some sense. But it's here, so I'll talk us through it. Maybe for some of you, this will be your preferred method. So I don't want to take that away from you. So to find your constant, we sort of said in the last video, the idea with this inverse variation is when you're multiplying the two values together, they're kind of always multiplying to the same number, right? Let me sort of talk through this maybe via this example. So this is current, right? So the current delivered to a circuit is 3 amps with a resistance of 8 ohms. Assuming the current and the resistance vary inversely, right? So they have this inverse relationship. Find the constant of variation and determine the current when the resistance is 10 ohms. Boy, I hope those are supposed to be amps and ohms and I don't sound like a nincompoop. So calculate the constant of variation here. So the idea is you've got 3 amps times your 8 ohms, right, is 24. That's your constant. The idea is just these two values that sort of have this inverse relationship. They're always multiplying to the same amount. If you want to think of this from sort of a geometry perspective, if you think of, I don't know, a rug or something, right, that has to sort of keep a certain area. So you have a rectangle. So you always want the same area for the rug. That means that if you sort of drop the width, you're going to have to sort of increase the length to compensate and vice versa. So the length and the width, if you have a certain like fixed area, are inverse. They have an inverse relationship, right? As one goes up, the other one goes down. So that's the same thing here with my current and my resistance. As the current goes up, the resistance will drop and vice versa, it seems. So the constant here is just this 24, right? And so what you're going to do there is say, well, anytime I have these two values, this current and this resistance, I'm going to hit 24. So if I find the constant, if I take my second situation, right, where the resistance is 10, the idea is, okay, so then in situation number 2, 24 is going to be 10 times my x, whatever I'm missing, and then you get to here, right, where you're doing quick just division by 10 to get your missing value. So that would be 2.4 amps, right? I think this is an Ohm's law thing, right? So if you are multiplying your current times your resistance, you get whatever the third thing is in Ohm's law. You guys are gonna have to tell me what that is. I'm just a humble math boy. I just crunch the numbers. If we use this to sort of solve one from the homework, in theory, this works for anything. A lot of the homework setups are very similar here, so I'm maybe not doing as many in the videos as I would otherwise. But let's look at number 9 from the exercises. This is gas mileage, right, miles per gallon versus drag, which we sort of said was one of our examples of an inverse relationship. As the drag goes up, the mileage will go down. So the gas mileage and the drag coefficient are inversely proportional, as we sort of just said. Currently, Jamie's drag coefficient is 0.07 when traveling at 55 miles per hour. His gas mileage is 22. So the 55 here is a value that you kind of need only to sort of establish that you're in the same situation. The relationship here is between the drag and the miles per gallon. If you add a roof rack, the drag coefficient is going to be 0.10 when you're going 55 miles per hour. So what will the new mileage be? What are the new miles per gallon? So the 55 is only there to sort of just confirm that you're sort of traveling at the same speed in both of these examples. We're not really going to use the 55 to solve this. So the information we need, right, is, so we could say, mileage versus drag at 55 miles per hour, right? It's just having a consistent sort of situation. So the drag was 0.07, and that gave us a mileage of 22 miles per gallon. If the drag goes up to 0.10, what is our new mileage going to be? What's our new miles per gallon? So to solve this with a constant, you're going to say, okay, so my constant is just whatever my first two values are multiplied to, right? So that's, for us, 0.07 times 22, right? So that's going to be 1.54. That's our constant. So then to solve this, right, my constant, 1.54, so that's going to be my new drag, 0.10 times my miles per gallon in situation number 2. So you can kind of see how this is, you know, maybe a little redundant. I don't want to talk badly about any kind of a math concept, right? But in theory, couldn't we get this same setup from just sort of doing the multiplication pairs? I would say, yeah. If we divide by this, it's just going to go up by 10, right? If we divide by 0.10, it's like multiplying by 10. So we get 15.4 as our new miles per gallon. That answer makes sense because it's dropped, right? What we're expecting is our miles per gallon to drop. As the drag goes up, it did, and it did. So I think we're on the right path. So that's the basics of it, right? It's in some sense the same setup over and over again. You can think of it in terms of this constant, or you can just use your multiplication pairs. Honestly, either is fine. The big mistake I see is everybody kind of wants to just keep doing proportions, and if you set them up as a proportion, you're definitely going to get the wrong relationship and the wrong value. So you just want to keep these inverse relationships separate from the direct relationships that we had in the last one. Anyway, that's it for skill number 8. We'll see you for skill number 9.